Hello everyone, this is Professor Ng Chi Kung from Unimas. In this video, I'm going to give you a lecture on approximate analysis of statically indeterminate frame with lateral loads using the Porter method. A building band deflects in the same way as a Porter frame. Each band of the frame can be considered as a series of Porters. So for example, this building band has two Porter frames like this. So in each of the Porter frame, the interior column would represent the effect of two Porter columns and would carry 2 times the shear V as the exterior columns. So in this building band here, we assume that it consists of two Porter frames like this. So the shear at the column here, or the shear inside the column, should be similar in each of the Porter frame. So if we join these two Porter frames together to form this building band again, so the shear in the internal columns here should be 2 times as compared to the exterior column. Okay, so meaning that the shear here and the shear here, the shear in the internal column is 2 times of the shear here and the shear there. And then for the Porter method of analyzing fixed support building frames requires the following assumptions. So a hinge is placed at the center of each girder. So in the middle of the girder, we assume that there is a hinge there, or the inflection point there, or the zero moment points, okay, in the middle of the girder. And a hinge is placed at the center of each column. So at the center of each column also, there is a hinge, okay. And then at a given flow level, the shear at the interior column hinges is 2 times that at the exterior column hinges. So in this particular assumption here, okay, we said that the shear in the exterior columns are just half of the interior columns, or the shear at the interior columns is double of the shear at the exterior columns. So with that, we look at a particular example here. Okay. So in this particular example, you are asked to determine approximately directions at the base of the columns of the frame using the Porter method. So for a frame that is loaded with a 6 kN force, B here, the deflection or the deflected shape of the column may look like this. Okay, so the girder may deflect this way, this way, this way. Okay, so hinges will be in the middle of each segment. So if the structure deflect like that, then we'll be expecting tension in this column AB here, tension in column CD, and then we may expect compression in column EF and also column HG, okay, because this force may lift this part of the structures and it may compress this part of the structure. So we may assume this column is in tension, this column is in tension, this column is compression, and also this column is in compression. So if we detach this structure at the hinges I, J, K and L, then he will look like this. Okay, so the unknown forces at I is a shear force V and an axial force Ij. So we assume that the internal force in this column, the axial force, is tension. So tension is the force going away from the hinge. So Ij is in the downward direction. Okay, and then the shear force here is V. Then the interior column, the shear force will be 2V. The interior column here, the shear force will be 2V, and exterior column here, shear force is V. Right? And then this column here, the axial force, we assume it to be tension, so tension is going away, so Jy is downward. And then for this column here, we said that this part of the structures, the column will be in compression. So compression is a force going into the hinge, and Ky is upward as well as for Ly. So after that, we have already put in all the unknown forces at the hinges, and we know that at hinges the moments are 0. So there is no more unknown moments at the hinges. So by using the equilibrium equations of total forces in the horizontal direction is equals to 0, then we will get 6 minus V minus 2V minus 2V minus V equals to 0. So in total we have 6 minus 6V equals to 0. So V is equals to 1 kilonewton. So in this solution we get positive, meaning that the assumed direction of V is correct. Okay, so this is 1 kilonewton from from right to left. This is 2 kilonewton from right to left, so on and so forth. So once we have solved this, now we want to move on to solve for the other unknown internal forces. So normally, by using the previous result, we proceed to dismember the frame at the hinges and determine their reactions. So as a general rule, always start analysis at the corner or joint where the horizontal load is applied. So here we have the horizontal force applied here. So we just detach further this hinge and isolate this as a free body diagram. So we get free body diagram like this. Okay, so V is already solved. So this is the known force already of 1 kilonewton. So the only unknown force is Iy, because we couldn't solve for Iy in this particular free body diagram because there are 4 unknowns and we have only 2 more available equations for this particular free body diagram, so we cannot solve for so many unknowns. So V we already know is 1 kilonewton, and then Iy we don't know. And then when we detach the hinge, there must be 2 forces, okay, one in the vertical direction and one in the horizontal direction. So these are internal forces in the girder here, okay, for segment BM. So the 3 reaction components at the hinges are determined by applying the 3 equilibrium equations. So all these my and mx direction, take note that my and mx, they are not moments. Okay, these are forces, okay, internal forces. It's a bit confusing to use m, but bear in mind that these my and mx, they are forces. Okay, so summing forces in the horizontal direction, we have 6 minus 1 minus mx equals to 0. So solving for that, we get mx equals to 5 kilonewton. And then to solve for my, we use total Fy equals to 0. But if we use this equation here, we have two unknowns, my and Iy. So we cannot use this equation first. Okay. So now let us move on to use a summing moment at joint M. Okay. So now you want to sum moment at joint M. Okay, joint M here. So let's start summing moment at joint M. And we take anti-clockwise moment as positive in this case. So for joint M, we have mx going through joint M, my also going through joint M, and 6 kilonewton force also passes through joint M. So these three forces don't create any moment about joint M. And then we have Iy, which is assumed to be a downward force, and Iy has a 2 meter moment arm to joint M. So Iy is creating an anti-clockwise moment about joint M. So Iy times 2 is the positive moment. And then we have this 1 kilonewton force having moment arm of 1.5 meter to joint M, and this force will produce clockwise moment about joint M. So minus 1 times 1.5. And there is no other moment, so we equate that to 0. Okay, so we have Iy times 2 minus 1 times 1.5 equals to 0. So solving for Iy, we get Iy equals to 0.75 kilonewton. In the solution, we get positive value, meaning that the assumed direction for Iy is correct, downward. Okay. So after getting Iy, now left only one unknown, which is my. So to solve for my, we may use the equilibrium equations of total force in the vertical direction equals to 0. So we have mx minus 0.75 equals to 0. So mx equals to 0.75 kilonewton. So with that, we solve for all the unknown forces in this particular segment of the building band, okay, or the building frame, okay, for segment IBM. Next, we move on to this particular part of the structure. Okay, so take note that this hinge is common to this free body diagram and to this free body diagram as well. So when you take the internal forces at these hinges, okay, they must be complementary to each other. So this is in accordance with Newton's third law. So Newton's third law mentioned that when there is an action, there must be a reaction of the same magnitude but opposite in direction. Okay. So take note that when we consider this part of the structure, this joint M is common to the joint M in this free body diagram here. Okay, so when we take this part of the building frame, okay, we detach this part of the structure from this hinge and this hinge here, so it will look like this. So as I mentioned, at joint M here and joint M here, they are the common joint, so the forces must be complementary to each other. So the force upward in joint M here, okay, is 0.75 kilonewton. Then it must be a downward force in this joint here. So that one is action, the other one is reaction. or vice versa. Okay, and then this horizontal force at joint M is 5 kN from left to right. So in this common joint M here, it must be from left to right, opposite of this direction, because one is action, the other one is the reaction, or vice versa. Okay, so we know that this force is 5 kN from the solution here, and this force is 0.75 kN from the solution here, but they are of opposite directions to the previous solution. So the only unknown force is Jy here, Nx and Ny. Okay, so similarly, we can use the three equilibrium equations to solve for the unknown forces. So first of all, we may sum total forces in the horizontal direction and equate it to 0. So we have 5 kN minus Nx minus 2 kN equals to 0. Solving for Nx, we get Nx equals to 3 kN and we get a positive solution, meaning that the assumed direction for Nx is correct. Okay, and then to solve for the other unknown forces, next solution, then we can just sum moment at joint N. Okay, so joint N here, we have 5 kN force, Nx and Ny passing through joint N. So these three forces don't produce any moment about joint M. So we have only this 2 kN force, 0.75 kN force, and Jy. Okay, creating moments about joint N. So let's just sum moment at joint N and equate it to 0, and take anti-clockwise moment as positive and clockwise moment as negative. Okay, so we have 0.75 kN force with 4 meter moment arm, and this produces an anti-clockwise moment about joint N. So we have 0.75 times 4, and then we have Jy with moment arm of 2 meter, and then Jy also produces anti-clockwise moment about joint N. So we have Jy times 2, and then we have this 2 kN force with moment arm of 1.5 meters about joint N. So this force will create clockwise moment, so minus 2 times 1.5. Okay, and then there is no other moments, and we equate that to 0, and solving for Jy, we get Jy equals to 0. Once we get Jy equals to 0, then next equation that we may use for the solution is total forces in the vertical direction is 0. So sum Fy, sum the forces in the vertical direction will be summing all the Fy and equals to 0. So in this case, we already have 0.75 kN here, and we already know Jy equals to 0. So we have minus 0.75 minus 0 plus Ny equals to 0. So Ny equals to 0.75 kN, and we get a positive solution. So Ny should be going upward, and we assume it upward in the first place, so we get a positive solution and it's actually going upward. Yeah? Okay, so next we move on to the other segments. So we move on to these segments here. So detach it from this joint and this joint here, and isolate this as a free body diagram. So we will be getting something like this. Okay, so take note that this joint N and this joint N, they are common joints. Okay, so meaning that the forces must be complementary to each other. One is action, the other one must be reaction, or vice versa. So Ny here is going up, then Ny here must be going down with the same magnitude. Okay, and then Ny here is going from right to left, and Y here must be going from left to right, opposite of this Nx, sorry, Nx, and this Nx here must be opposite of this, but with the same magnitude. Okay, and then this three-body diagram, the only unknown is Ky, Ox, and Oy. So similarly, using the three equilibrium equations, you may solve for Ox, Oy, and Ky, and after that, this joint O is the common joint with this joint O is common to this and this. Okay, so this joint O is common in these two free body diagrams. So the forces must be in the same magnitude but opposite direction. Okay, so this OY is upward, this OY must be downward. And then using the two equilibrium equations, then we may solve for Ly. Okay, and then this is V. This is also a known force. The only unknown is Ly. Then we just sum forces in the vertical direction. So we have negative 0.75 plus Ly equals 0. So Ly equals to 0.75 kilonewton. Okay, so now we have already solved for all the unknown forces of Iy, Jy, Ky, and Ly. And we have also the shear forces of V, 2V, 2V, and V there. So next we'll move on to the bottom part of the structures. So now we want to move to the bottom part of the structures. Okay. So the bottom part of structures, the free body diagram will look like this. Okay. So for segment IM, for segment IA, okay, we have a dimension of 1.5 meters. Okay. And then this joint I here is the common joint as this joint I there. So the forces must be complementary to these two forces here. Okay. So the shear must be going from left to right here, 1 kilonewton, and then the internal forces in the column is going up 0.75 kilonewton. Okay, because one is action, one is reaction. So this 0.75 kilonewton must be in the opposite direction to this one. Okay, so these are known forces. So the only unknown forces are Ax, Ay, and Ma. Okay, so for each free body diagram, if we only three unknowns, then we have three equilibrium equations, so we can solve for the unknowns. Okay, so Ax is assumed to be from right to left, Ay is assumed to be downward, and then Ma is assumed to be anticlockwise. Okay, so to solve for Ax, okay, we just sum total forces in the horizontal direction. So if we have 1 minus Ax equals to 0, so Ax equals to 1. So positive solution, meaning that Ax is correct in this direction. And then we sum total forces in the vertical direction. So we have 0.75 minus Ay equals to 0. So Ay equals 0.75 kilonewton, and it's downward. And then to solve for Ma, we may sum moment at joint A, okay, or you may sum moment at joint I. Both will give you the same solution. So now we just sum moment at joint A and take anticlockwise moment as positive. So we have Ma, which is anticlockwise, okay, and then these two forces of Ay and Ax, they both passes through joint A, so they don't produce any moment. This 0.75 kilonewton force also passes through joint A, so this force also doesn't create any moment about joint A. So left only this 1 kilonewton force with 1.5 meter moment arm, and this force will cause clockwise moment about joint A. So the moment is negative 1 times 1.5. So MA minus 1 times 1.5 equals to 0. So we get MA equals to 1.5 kilonewton meter. So we get a positive solution from the equilibrium equation, so meaning that the assumed direction for MA is correct as an anti-clockwise direction. So similarly, the other three segments of the columns, we may analyze it using the three equilibrium equations for each of the free body diagrams. And take for example this joint J here is the common joint as this joint J over here. So here we have a shear force 2 kN from right to left. Then the shear force must be from left to right of magnitude 2 kN here. And then Jy from here is 0. So no more vertical force in joint J here. Okay. So supposedly there is a horizontal, not horizontal, so it should be a vertical. There must be a vertical reaction here, Cy, but since there is no other vertical forces, so Cy is equals to 0. Okay, and then Cx is equals to 2 kilonewton using the equilibrium equations of summing the horizontal forces equals 0, and then Mc equals to 3 kilonewton meter by summing moment at joint C or summing moment at joint J. Both will give you the same solution. So we may use the similar method to analyze for ME and EX, and then MH, HX, and HY. Okay, so that's all for the lecture in this video. Thank you very much for watching.